Welcome back to my journey through real analysis. In this video, we'll be going over some proofs involving sequences. This was harder than expected, mostly because I'm not used to proving things within some open ball. So without further ado, here are the proofs. Let's start with a refresher on the convergence of sequences. So here, again, the definition is that a sequence AN converges if the tail of that sequence is contained within an open ball. And so we conceptualize that by saying, sorry, we're out of focus all of a sudden. There we go. This is conceptualized by this difference. So the element AN, after we're in this open ball, minus the limit point is less than some epsilon for every epsilon. And we will see this come up in the proofs that we go over. First proof. So a sequence converges. There we go. First proof. A sequence converges to 0. So we have to show that the square root of that sequence also converges to 0. So we can begin with the definition of convergence. And really, I just took that definition and then plugged in xn and 0. And I want to make that less than epsilon squared. That will become apparent later in the proof. Notice how I would take the square root of both sides and that epsilon squared becomes an epsilon. And then note that the square root here is equal to that. And this is namely because this is positive. If this were negative, then this would not be true, because I'd be taking a square root of a negative, and then this would be a complex analysis class all of a sudden. So observe that this is true, this sequence of algebra steps, and because the square root of n is less than epsilon, I can then conclude that this is within the same neighborhood and it converges to 0. So this proof, not too bad. The one beneath it required some effort. So same basic idea, except for the fact that, this shadow is my camera. Except for the fact that this goes to a limit of x, and then this goes to a limit of x squared, or the square root of x. And so first, notice some algebra. So I took the resulting place, which is this guy. So this is what we want to prove converges to the square root of x. And I did some algebra. So this is multiplying by 1. This simplifies to this. And I know that this converges. This is in our theorem. So I'm assuming that this is true. So I know that I want the n as it goes to infinity. So as this gets closer and closer to this limit point, this xn will be very, very close to the square root of x. So I know that this is greater than just the square root of x, which is equal to the square root of x. Right. This seems fairly obvious. However, we can use that in our proof. And so here, this fraction is less than or equal to this fraction. You can deduce that by taking the reciprocal of this guy and the inequality flips. Okay. Now I feel like we're able to actually write down the proof. So notice that since this is going to x, for all delta, this is the delta, there is a neighborhood such that this is less than delta. And so in this case, let delta be equal to epsilon square root of x. So therefore, our original want, square root of xn minus square root of x, is equal to this. We did that earlier, which is less than this. We did that earlier as well. But now notice how xn minus x is bounded by epsilon at square root of x. So this is equal to epsilon. So then I proved that this is less than epsilon. And then I just used the definition of convergence here. So that's really this proof. Sorry, this looks like a wall of text on the camera. Okay. This is the shuffle sequence problem. So let xn and yn be given. And then xn is the shuffle sequence where it alternates between x1, y1, x2, y2, so on and so forth, xn, yn. So I want to prove that xn is convergent if and only if xn and yn are convergent with the same limit. Okay. So let's assume that xn is convergent. Then this is just the definition of convergence. And then we can observe that the tails xn and yn are contained in that same open ball. And so we know this because of the way that x or zn is defined up here. And so then that means there exists n sub x and y sub x, their own open balls, respectively. And so therefore I get to write these two things. And because they're in the same open ball, the limit exists. So this one's really just a consequence of observing that the tail of the sequence converges together to the same limit, only because z of n converges. The trouble here was just writing it formally as a proof. And then the inverse is also true. So let x and yn be convergent, and let the limits be the same. And so I just apply the definition of convergence. For all epsilon, we find an nx whenever nx is greater than n. For both n and y, they have their own open balls, right? So also, this is true as well. This is also an assumption. So if I set n equal to the maximum of both of my open balls, like where they begin, for all epsilon greater than 0, I have this relationship such that this is true. And I know this is true because Zn is defined to be the shuffled sequence, and they converge to the same limit. So Z sub n is in the same neighborhood as of xn and yn, so this inequality is true. That's all I have to share today. The way the books are going, we will get into subsequences and infinite series soon enough, so stay tuned for that. Thanks for watching.